Ever wondered how AI models like GPT, Llama, or Vicuna decide what's safe to say? Or why some harmful content still slips through their filters? Today, we're exploring a groundbreaking study that exposes a critical vulnerability in AI safety systems, revealing how attackers can manipulate the very language map these models use to understand the world. Let's break down the science behind this discovery. Imagine a world where AI is trained to avoid toxic or dangerous outputs. These models are safety-aligned, right? But what if someone could subtly alter the model's internal map of words and meanings, its embedding space, to make it ignore its own rules? That's exactly what this research uncovered. So what's an embedding space? Think of it as a mathematical representation of language, where every word, phrase, or concept is mapped as a point in a high-dimensional space. The closer two points are, the more similar their meanings. For example, cat and kitten would cluster together, while cat and rocket would be far apart. This space isn't just a dictionary. It's the model's neural network's way of understanding relationships between ideas. Now, safety alignment mechanisms act like a guard dog, flagging inputs that might lead to harmful responses. But this study shows attackers can poison this embedding space, slipping in tiny, almost invisible changes to word representations. These tweaks don't alter the model's training data or code, but they trick the model into thinking a toxic prompt is harmless. The researchers call their tool ETTA, Embedding Transformation Toxicity Attenuation. Here's the magic. Instead of brute-forcing safety checks, ETTA identifies specific toxicity-sensitive dimensions in the embedding space. It's like finding the right knobs to turn in a machine to make it malfunction. By subtly adjusting these dimensions, ETTA makes harmful inputs look benign to the model, all without retraining the AI or touching its code. Think of it like a sneaky filter. If you wanted to bypass a spam filter, you wouldn't rewrite the whole email. You'd tweak a few words to make them look normal. ETTA does something similar, but in the complex world of AI embeddings. It's not about breaking the model. It's about exploiting the way it interprets meaning. The results? Mind-blowing. ETTA achieved an 88.6% success rate across 5 major open-source models, outperforming existing attack methods by over 11%. Even models with extra safety layers, like instruction-tuned versions, couldn't fully block it. And here's the kicker. The attack didn't trash the model's overall performance. It only caused a minor drop in tasks like fact-checking or math problems. But how does this work exactly? Let's zoom in. Researchers discovered that toxic words aren't isolated in an AI's mind. They're deeply tied to the meanings of other words. By tweaking the embedding space, attackers accidentally messed up both harmful content and innocent words nearby. It's like if a single bad ingredient in a recipe made the whole dish taste wrong. Except here, the AI's recipe for understanding language gets scrambled. This isn't just about tricking AI. It's about understanding how these systems think. It highlights the delicate balance between keeping AI safe and letting it be useful. After all, if we can manipulate how models perceive language, we might also find ways to improve their safety. But it also raises a big question. How do we protect against attacks that exploit the very architecture we rely on? The study also uncovered some surprising flaws. For instance, some attacks cause the AI to repeat the same nonsense over and over. Repetition collapse. Or they might twist the meaning entirely, like turning "teach kids to use guns" into "create a video game about firearms." These errors happen because the attack focuses on tricking the AI's first reaction, not its full understanding. So what does this mean for the future of AI? It shows that while attackers are getting clever, AI safety is evolving faster. Researchers are uncovering weaknesses, but also proving that modern models have robust defenses. The takeaway: AI safety isn't a fixed rule. It's a constant game of cat and mouse, where each side learns from the other. And as we push the boundaries of what AI can do, we must also ask, how do we build systems that are both powerful and secure? The next time you interact with an AI, remember, behind every response is a complex web of language, math, and safeguards. And as this research shows, even the most advanced systems aren't immune to the cleverest of tricks. Stay curious, stay informed, and keep questioning how the AI in your life really works.